Alrighty. In this video, we are going to go ahead and work on more on Lagrange error. Number 5 is no calc. We have f is equal to the sum of its Taylor series for all values of x. And we have the graph of the absolute value of the fifth derivative is shown below. We have the fourth degree Taylor polynomial for f about x is equal to 0. And we want to use information from the graph to show that my error is less than 1 over 6,000. All right, so we have a fourth degree Taylor polynomial. Since we have a fourth degree Taylor polynomial, this tells me that my error means that I'm going to have to use my fifth derivative of z. I'm going to have x minus c to the fifth, and then I have 5 factorial. And I want to show you that that is going to be less than 1 over 6,000, which is kind of crazy. X is going to be 1/4 just because my center is at 0. So I might as well do this 1/4 right here. And then lucky for us, they gave us the derivative of the fifth derivative right here. And we want to approximate it between 0 and 0.25. Well, looks like 0.25 is going to be my maximum, and that looks like it's about 18-ish. Now, we're not going to be using 18-ish just because that's going to be a nasty number, but we do know that 18 is less than 20, so I'm going to use 20. Because that's going to make my life a little bit easier. We know that that's going to be 20. We have 5 factorial. Remember that 5 factorial is 120. And then we have 1 over 4 to the 5th. 4 to the 5th, I think, is... I can't do that on my head. But I know that that's going to be the same thing as 2 square. So that's going to be 2 to the 10th. And I know what 2 to the 10th is. 2 to the 10th is 1,024. That's going to be less than, let's see, 20 over 120 is going to be 1/6. Now we are going to multiply 6 and 1,024. Remember that this is calculative. 24, 6, 12, 4. So you're going to get 6,144. And we know that right there. Let me shrink this. That right there is going to be definitely less than 1 over 6,000. Yay. So if they give you a table, go ahead and probably approximate this using whatever they give you from 0 to 1/4 in this case. Now let's say that they give you a table here instead of a graph. 6 says let h be a function with derivatives of all orders for x. Selected values of h and its derivatives are given. H prime x is decreasing from 0 to 2. And I'm not going to be focusing on A and B. I'm only going to focus on part C because that's going to be my Lagrange error. Part C says, use the Lagrange error bound to show that the third degree Taylor polynomial for h about x is equal to 1 approximates h of 0.9 with error less than 2 to the negative 4. Okay, so we have h of 0.9, which is my function. Then we have my Taylor polynomial, my third degree Taylor polynomial, that I really don't care about, but it's just there. And then I'm going to get my error. Well, my error, remember, is going to be my next derivative. So that's going to be my fourth derivative at z, x minus c. X is going to be 0.9. C is going to be 1, since that's my center. This is to the power of 4 over 4 factorial. Okay, so I need to figure out what my fourth derivative of z is. Well, if I were to look at my table here, lucky us, they gave it to us. Yay. Because they gave it to us, we know that my fourth derivative at z is going to be 144 over 5. So now I have 144 over 5. And then that's going to be 0.1, so 1/10 to the 4th over 4 factorial. Now this is a calculator inactive problem, so you kind of do need to simplify this so that it's a little bit pretty. Okay. Let's see. Four factorial is going to be 4 times 3 times 2 times 1, which is 24. So I'm going to rewrite that as 24. And then I'm going to have that 5 right here. 24 over 5, 24 times 5, well, that's just 5 factorial, so that's 120. So this is 120. Okay, now 144 over 120, let's try to simplify that. That's like 72, 60, 36, 30, 6 over 5. So that's going to be 1.2. Let me go ahead and shrink this again. So now I have 1.2 and then 110 to the 4. Well, if I were to think about this here, 110 to the 4 is the same thing as 10 to the negative 4. And 2 to the negative 4 is going to be 2 times 10 to the negative 4, which we clearly see in terms of our lovely scientific notation, that 1.2 times 10 to the negative 4 is less than or equal to 2 times 10 to the negative 4. So we know that this is definitely, the error is less than 2 to the negative 4. And that's my work there. Cute. Let's do 9. We want to estimate e to the 1.45 using a Taylor polynomial centered at x is equal to 2. And we want to find out the least degree of polynomial that assures an error less than 0.001. Okay. Once again, I don't know what my degree is, so I'm kind of screwed a little bit because now I have to do n plus 1 of z, x minus c. X is 1.45, z is 2, n plus 1 over n plus 1 factorial. And that has to be less than 0.001. Lucky for us, since we are technically using e to the x, and we are finding the derivative there, my derivative of e to the x is just going to be e to the x. And then if I were to think about 1.45 and 2, I know that 2 is definitely going to be larger than 1.45 in terms of e to the x. So this one was kind of lucky because we kind of knew what that was in terms of e to the x. So now I have f, or this actually, being e to the 2. And then we have 0.5, negative 0.55, n plus 1 over n plus 1 factorial. And that's going to be less than 0.001. Now, your job is to figure out what the value of n is and then call it a day for number 9. I'm not going to do that. You could also check the answer key in the student notes and see what that is. Number 10 seems fun. All right, number 10, a Taylor polynomial centered at x is equal to 3 for f is given by p sub 3x is equal to that lovely thing right there. Part A says, show that f has a critical point at 3. Does this critical point correspond to a relative max, a min, or neither? And we want to justify our answer. So, once again, you'll notice that we don't have a degree of 1 right here. Because we don't have a degree of 1, this tells me that my derivative at 3 is going to be 0. Now, it says show that, so basically you kind of need to look at your Taylor polynomial and say that, okay, we have 0 is equal to f prime of 3 over 1 factorial. In that case, f prime of 3 is 0. Now, because that is 0, we can use my second derivative test, and that we could use because that's going to give us negative 9 is equal to f double prime of 3 over 2 factorial, which tells me that I get negative 18. Now, because my second derivative is negative, this tells me that the function concaves down. So the function, well, because f double prime of 3 is negative, the function concaves down at x is equal to 3, which means there is a local maximum at x is equal to 3. Part B says, use my Taylor polynomial to approximate f of 1. Well, that one is easy. You're just plugging in 1, okay? So f of 1 is approximating p sub 3 of 1. And that's going to be equal to 7 minus 9, negative 2 squared, minus 3, negative 2 squared to the third. And then find out what that is and call it a day. What is it? I don't know, but it's that right there. Okay, C. The fourth derivative of f satisfies this lovely thing right here. So notice that they gave you this right here, which is very good because whenever we're doing my error, I know that my maximum is going to be 5. Okay, part C says justify that f of 1 cannot be positive using Lagrange error. Okay, so we have f of 1 minus p sub 3 of x, and that's going to be less than or equal to my derivative, my fourth derivative, my maximum fourth derivative, in this case it's 5. My center is at 3, so that's going to be 3 minus 1, which is going to give me 2. And then I have 4 factorial. All right, so we know that 4 factorial is going to be 24, and then 2 to the 4th is going to be 16. And if I were to do that, that is going to give me, let's see, six, 2, 3. So 10 thirds, that's going to give me 10 thirds. Let's see this, 10 thirds. All right, now that's not my question. My question says justify that f of 1 cannot be positive using Lagrange. Okay, I have 10 thirds. I have my Taylor polynomial, my third degree Taylor polynomial, and I have f of 1. Well, here's the bad news. We actually do need to find the approximation for f of 1 for p sub 3 of x so that we could plug it in here. The reason why is because I want to find out what f of 1 is, and I want to prove that this can't be positive by using whatever value this is, and then solving that inequality. 9, 4, 3, negative 8, 36, 24. 7 minus 36 is negative 25, no, negative 29, and then plus 24, so that's going to give me negative 5. So this means that my Taylor approximation at 1 is negative 5. And that's going to be less than or equal to 10 over 3. I'm going to solve this inequality now. So I have negative 10 over 3 is less than or equal to f of 1 plus 5, which is less than or equal to 10 over 3. I'm going to subtract 5 from both sides, or in this case, 15 over 3 on both sides. And that's going to give me my approximation of f of 1. Well, on the left side, that's going to be negative 25 over 3. And then on the right side, that's going to give me negative 5 over 3. Based on that information right here, this tells me that f of 1 can't be positive, because it's squished between negative 25 over 3 and negative 5 over 3, both being negative. So this tells me that, hey, f of 1 cannot be positive using Lagrange. All right. The other problems are basically going to be the same thing. There's like 20 of them just because I'm saving some of these for the practice day on the ACT day. So, do all 20 now or do all 20 whenever we have the ACT day, and we'll call it a day. I'm not sure if the 5-in-1 will include error, but it most likely will. But obviously this will be on the test. After this, we are going to start Unit 4A, which is on parametrics.